This is the IEE573 term project. I'm Henry Gomez. I'll be presenting the material and work done by myself and Jimena Enriquez. In this presentation we will be covering the following items. We'll go through a problem description, root cause analysis, a description of the data, the proposed analysis that we went through here, along with a literature review along the topics of this particular failure mode, data analysis summary, an application of the results, and finally a conclusion with some suggestions for fixing the root cause issue. We're going to start off with the problem description. In this case we have company XYZ, which shipped many products with a memory controller which is designated as the J controller. This particular controller had an issue that was undiscovered during time of manufacturing and came about during field use. The affected time period for this particular failure mode is from January 2005 through October 2006. In this time period, the products exhibited a higher than expected field failure rate. The root cause was unknown until further investigation was implored, and at that time the failure mode was determined to be a data retention failure in the NOR flash portion of the controller. Data retention in this case was caused by a charge loss of a single bit in the NOR flash that caused a charged cell to transition to an uncharged state, or basically from a value of a 1 to a 0. The root cause of the failure mode was higher than expected leakage of the NOR cell. You can see here in this diagram is a cross section of the NOR cell gate, where we have basically the word line, the floating gate, the source line, and the bit line. This is a functional cross section of one of the many cells contained within the NOR flash. It is believed that the defect failure mode was attributed to gate oxide defects, which were caused by an ion implantation stage during the processing of the NOR gates. The affected area of this functional cell is highlighted with the red arrows and circles. Basically the oxide defects that were caused during the ion implantation stage caused the cells to dissipate their current over time, again characterized by a charge loss or a bit flip from a 1 state to a 0 state. For this particular project we had two sources from two different populations for the data analysis. The first population was the field returns from an unscreened population. Now an unscreened population in this case is the initial time period of the product release where no defect was known or discovered. So this population of parts again come from a set of and time period where a problem was not suspected, and the data that we have represents field failures from normal use conditions without any test screens for this particular issue. The second population that we have comes from a screened population. Basically what has occurred in this time period is we have become aware of the issue, and a test screen was implemented to basically eliminate the failure population from entering the field, and what we found is that effectively this screen was not as effective as first thought, and failures continue to occur. So we have data from this time period also. And then we also have data from accelerated life test, or ALT, for both populations of unscreened parts and screened parts. So the issue at hand here is that company XYZ has shipped several thousand units into the field. Many units did not receive any test screens. Some received test screens but continue to fail and did not receive the total root cause fix. So the thousands of units in the field are still failing. So we need to understand the implications of this particular failure mode. We need to understand if a screening process can be implemented. We need to understand the type of distribution or time frame we can expect these failures to follow in order to better recommend to company XYZ the actions needed. Actions can be several different things. Actions can be leave the parts in the field and let them fail and replace upon failure to the customers if it's a small nuisance factor type failure mode. If it's a catastrophic type failure mode, then a total recall may be necessary. So it's appropriate for us to start our analysis by looking at the field impact of the affected population, looking at the failure mode distribution, determining the failure rate, and also determining the activation energy, which will all lead us to coming to conclusions in terms of proper test procedures along with handling of parts in the field. Again, the goal of this risk assessment that we will be performing is to determine the burn-in test plan and other solutions. During the course of this project, we not only had data at our disposal, but we also conducted a very thorough literature review for this particular failure mode. NOR flash memory is not a new cutting-edge technology. It's been on the market for a while. So both myself and my partner embarked on an extensive literature review to determine if we could come up with dominant failure modes for NOR flash, to see if what the failures that we will be analyzing are in line with what the industry has studied and the expected failure modes for this particular type of flash. Also, our investigation was aimed at finding a particular, if there was any baseline activation energies that we can use or compare our analysis to. So to start off with our literature review, again, what we found is that data retention is inherent to NOR flash memory devices. So basically, the failures that company XYZ is experiencing is actually an inherent failure, an intrinsic type failure common to NOR flash. Then that brings us to a key question that we need to keep in mind during our analysis is that whether the populations that we're studying, if they are in line with what is to be expected, or is there something else occurring that's accelerating the failure mode. In terms of failure modes, we also found during our literature review the top failure modes for NOR flash. Again, the first being charge retention, in which defects in the dielectrics or substrate charges can move to or from the floating gate, causing elevated charge loss. Basically, we have defects in the dielectric that cause leakage paths for electrons to move or discharge from one state to the next. The next failure mode that we found is also an oxide degradation. Basically, high fields that are used during program and erase cycles in the NOR flash can cause or result in an increased low field leakage through the dielectrics of the cell. This again can increase the susceptibility to charge loss of the cell. Again, the failure mode is an oxide degradation, but the symptom would also be a data retention loss, or basically a flip of a bit from a charged state to an uncharged, a 1 to a 0. We also found that a dominant failure mode within a NOR flash component is a program erase time degradation. What we have here is that basically after a large number of write erase cycles, a high charge can be trapped in the dielectrics surrounding the floating gate. This charge can decrease the effective field across the cell during program and erase operations, thus increasing the time required to complete the program and erase operations. We can see that in this particular case, this failure mode is not applicable to the data set that we're studying here and the issue that company XYZ is experiencing. The next failure mode is a write disturb. This is pretty dominant also in NOR flash memory. A write disturb occurs during the program operation, in which high fields are placed not only on the bit being programmed, but on other bits along the same word line and or bit line. If there are defects in the dielectrics or in the substrate, leakage paths can be created, so inadvertently programming of a non-selected bit can be observed. So this is data that we found from Samsung Semiconductor application report on NAND memory from 1998. In this particular failure mode, although it does contain defects in dielectrics, and which is some of the applications that we're studying here in this particular failure mode with company XYZ, we can see that the data that we have is not a write disturb failure mode, in that we're not trying, the failure symptoms that we're seeing from company XYZ are not that of a wrong bit being programmed, rather a transition from a charge state to a charge loss state. So also we feel that this particular failure mode is not applicable to our study. So we're centering our literature review around charge retention and our oxide degradation, as they seem the two highly most likely failure modes or dominant failure modes leading to a data retention issue, such as we're studying here in this term project.